everyone, we are Group 8 and we are here going to discuss about the things about antenna and its functions. And through those learnings, we will share you an antenna we've designed. So, as an introduction, we must first define what is an antenna. So, an antenna is a device made of conductive material that sends or receives electromagnetic radio waves. Electromagnetic radio waves are waves of light within a specific frequency, which is 3 kHz to 300 GHz, that are invisible to the human eye and are utilized for long-distance communication. These waves are intercepted by your antenna, which properly displays the sound within the wave. So now that we know what an antenna is, why don't we go back to its roots on how antenna was discovered and when it started through its history. So, it was during the time of the 1830 when Faraday slid a magnetic around the coils of a wire attached to a galvanometer. In moving the magnet, he was in effect creating a time-varying magnetic field, which as a result must have had a time-varying electric field. The coil acted as a loop antenna and received the electromagnetic radiation which was received by the galvanometer, the work of an antenna. Interestingly, the concept of electromagnetic waves had not even been thought up at this point. Then, in 1886, Heinrich Hertz developed a wireless communication system. So, first, this is Faraday, and then this is Heinrich Hertz. Continuing, in which he forced an electrical spark to occur in the gap of a dipole antenna. He used a loop antenna as a receiver and observed a similar disturbance. By 1901, Marconi was sending information across the Atlantic. For a transmit antenna, he used several vertical wires attached to the ground. Across the Atlantic Ocean, he received antenna was a 200-meter wire held up by a kite. And then in 1906, Columbia University had an experimental wire station where they used a transmitting aerial cage. This was a cage made up of wires and suspended in the air resembling a cage. So, for additional information, in the year 1920, Yagi-Uda antenna was discovered. The Yagi-Uda antenna or Yagi antenna is one of the most brilliant antenna design. It is simple to construct and has a high gain, typically greater than 10 dB. The Yagi and Uda antennas typically operate in the HF and UHF bands, although their bandwidth is typically small, on the order of the few percent of the center frequency. The Yagi antenna was invented in Japan, with results first published in the 1926. The work was originally done in Shintaro Uda, but published in Japanese. The work was presented for the first time in English by Yagi, who was either Uda's professor or colleague, who went to America and gave the first English talks on antenna, which led to its widespread use. Hence, even though the antenna is often called a Yagi antenna, Uda probably invented it. And then, in 1939, the horn antennas were made. Horn antennas are very popular at UHF, which is 300 MHz to 3 GHz, and higher frequencies. Horn antennas often have a directional radiation pattern with a high antenna gain, which can range up to 25 decibels in some cases, with 10 to 20 decibels being typical. Horn antennas have a wide impedance bandwidth, implying that the input impedance is slowly varying over a wide frequency range. The gain of horn antennas often increases as the frequency operation is increased. This is because of the size of the horn aperture is always measured in wavelengths. At higher frequencies, the horn antenna is electrically larger. This is because a higher frequency has a smaller wavelength. And a recurring theme in antenna theory is that larger antennas have higher directivities. Horn antenna have very little loss, so the directivity of a horn is roughly equal to its gain. Horn antennas are somewhat intuitive and relatively simple to manufacture. In addition, acoustic horn antennas are also used in transmitting sound waves. As an example, a megaphone. Horn antennas are also often used to feed a dish antenna or as a standard gain antenna in measurements. Then in 1940, have antenna arrays. An antenna array is a set of two or more antennas. The signals from the antennas are combined or processed in order to achieve improved performance over that of a single antenna. The antenna array can be used to increase the overall gain, provide diversity reception, cancel out interference from a particular set of directions, steer the array so that it is most sensitive in a particular direction, determine the direction of arrival of the incoming signals to maximize the signal to interference plus noise ratio. Parabolic reflectors after that is then made in the 1940s. So parabolic reflectors typically have a very high gain and has a low cost polarization. They also have a reasonable bandwidth, with the fractional bandwidth being at least 5% on commercially available models, and can be very wideband in the case of huge dishes. The smaller dish antennas typically operate somewhere between 2 and 28 GHz. The large dishes can operate in the VHF region, but typically need to be extremely large at this operating band. Then, in the 1970, patch antennas were created. So, a patch antenna is a type of a radio antenna with a low profile, which can be mounted on a flat surface. It consists of a planar rectangular, singular, or any geometrical sheet or patch of metal mounted over a larger sheet of metal called a ground plane. And then lastly, in 1980, PIFA, or known as planar inverted F antenna, consists of a rectangular planar element located above a ground plane, a short-circuiting plane or pin, and the feeding mechanism for the planar element. The inverted F antenna is a variant of the monopole where the top section has been folded down so as to be parallel with the ground plane. This is done to reduce the height of the antenna while maintaining a resonant trace length. This parallel section introduces capacitance to the input impedance of the antenna, which is compensated by implementing a short circuit stub. The stub's end is connected to the ground plane. So that's it for my part.
Hello everyone, I am Jen Valenton and I will be discussing about this antenna function. So we all know that antennas have many different uses. So from Wi-Fi to radio, but they are all work in fundamentally the same way. Transmitter sends a signal which is intercepted by a receiver. So listening to music inside a vehicle starts with a radio station with a large radio transmitter. As we all know, the transmitter functions by taking audio, such as current. This electrical current then flows vertically along a radio tower to the top where it makes electrons, charged particles inside of an atom. So this creates electromagnetic radio waves and sends them hundreds of miles. So electrical equipment broadcasts the electrical current at a specified frequency. We can say at 101.5 megahertz. These waves are then received by radio receivers. So these radio receivers have antennas that are connected to tuners. And then these tuners look for a specific frequency of radio waves. If you tell the tuner to look at 101.5, the frequency that we've got earlier, so the tuner receives the incoming radio waves and the amplifier takes over. The amplifier boosts the sound so you can hear the music inside your car. Next slide, please. So, as we all know, antennas are much more than simple device connected to every radio. They are the transducers that convert the voltage from a transmitter into a radio signal. And they pick radio signals out of the air and convert them into a voltage for recovery in a receiver. Next slide, please. What is radio waves? Just what is a radio wave anyway? A radio wave is a combination of magnetic field at a right angle to an electrical field. Both oscillate at a specific frequency and they travel together in a direction perpendicular to both fields. So these electromagnetic fields move at the speed of light through free space. So according to Maxwell's well-known equations, they support and regenerate one another along the way, but we can't over distance. Next slide, please. What are some of the characteristics of a radio wave? One of the key features is the orientation of the fields with the Earth. This is called the polarization. An antenna is vertically polarized if the electromagnetic field is vertical to the Earth's surface. The antenna is horizontally polarized if it's horizontal to the Earth's surface. So that is the characteristic of a radio wave. Next, please. Are there any other critical features of a radio wave? Generally, radio waves have a near field and a far field. The near field is close to the antenna, usually within several wavelengths. The far field is about 10 wavelengths or more than from the antenna. So the far field breaks away from the antenna and becomes the radio signal. Applications with regards to these communications and near field communications use the near field, which is more akin to the magnetic field around a transformer primary winding. But overall, the far field is the most useful radio wave. Next, how does an antenna work? The antenna, the transmitter, generates the radio wave. It is observed that a voltage at the desired frequency is applied to the antenna. The voltage across the antenna elements the current. Through them, it creates the electric and magnetic waves, respectively. At the receiver, the electromagnetic wave passing over the antenna induces a small voltage. Thus, the antenna becomes the signal for the receiver input. Next, will the same antenna work for both transmit and receive? The answer is yes. We call the antenna reciprocity. Any antenna will work for either transmit or receive. In many wireless applications, the antenna is switched between the transmitter and receiver. Next, will a vertical antenna receive a horizontally polarized signal or vice versa? In most cases, it is a yes. In real world, antennas are rarely perfectly horizontal or vertical, so some signal is received. Furthermore, most signals undergo shifts in polarization over the transmission path due to reflections and other multipath conditions. Yet, this antenna orientation mismatch does introduce some attenuation. Next is, what is circular polarization? Just as the name implies, the polarization rotates continuously during transmission, making it possible to use either horizontal or vertical antennas for receiving. In maximum reception, A circularly polarized receive antenna is needed. You also can have an antenna that produces right-hand or left-hand circular polarization. So this again allows frequency reuse by using different polarizations on two different signals. Often, a helical antenna made of a spiral conductor and reflector is used. In a circular polarization is most commonly found in satellites. Next, please. So how does the radio signal propagate from transmitter to receiver? Signals move from one antenna to another in several ways. Based on the radio wave's frequency, at low frequencies, propagation is by ground wave where the signal hugs the Earth's surface. Distance is limited to 100 miles or so. We all know that AM radio waves are a good example of low frequency propagation. And based from frequencies, signals travel 30 to 250 miles into ionosphere, where they're refracted back to Earth. It's almost like radiating the signal so that it appears to be reflected off of a conducting surface. Very long distances can be achieved as signals can make several hops from the Earth to the ionosphere and back several times. So that's it for my part. And yeah, next is types of antennas.
Hello, I'm Galen Bordonada, and I will be discussing the different types of antennas. Next slide, please. Wire antennas are one of the most commonly used antennas and comes in different shapes and sizes. These are used in vehicles, ships, and buildings. Here are some examples of wire antennas. Next slide, please. So first we have the dipole antenna. The name dipole, if we were to break it down, di and pole, it means that it is made up of two poles or two conductive elements in the same axis. The length of the wire needs to be small compared to its wavelength. This type of antenna also has its subtypes. Next slide, please. There. The short dipole antenna is a subtype of the dipole antenna. In its simplest form, it is basically an open circuit wire with the signal being fed at the center. The term short in short dipole antennas doesn't directly refer to its size, but rather to the size of the wire relative to the wavelength of the signal. Typically, the length of the wire is less than the tenth of the wavelength of the frequency of operation. Next slide, please. Next, we have the monopole antenna, which is one half of a dipole antenna, which is almost always mounted above some sort of ground plane. Next slide, please. Lastly, for the wired antennas, we have the loop antenna, which is considered as a high directional antenna, which is commonly used in a directional finder equipment. It is formed by a single or multiple turn of a wire that forms a loop. The radiation pattern of a loop antenna is similar to a short dipole antenna. The shape that you can see here is only one of the shapes possible for a loop antenna, and there are also other ways that you could form a loop antenna. As long as it forms a loop, it can be of different shapes, and you will still get the same result. Next slide, please. The next type of antenna we have is the aperture antenna, which is an antenna with an aperture at the end. The edge of a transmission line, when terminated with an opening, radiates energy. This opening, which is an aperture, makes it an aperture antenna. Here are some examples of aperture antennas. Next slide, please. So first we have the slot antenna, which is an antenna that is formed by making a cut on the surface where it is mounted on and have radiation patterns that are roughly omnidirectional. It also works exactly like a short dipole antenna. Next slide, please. Then we have the horn antenna, which is a popular type of antenna at ultra-high frequencies and has a directional radiation pattern with a high antenna gain. It is constructed in a variety of shapes such as sectoral E-plane, sectoral H-plane, pyramidal, conical, and etc. It is used as a feed element for large radio astronomy, satellite tracking, and communication dishes. A common element of phased arrays, it is also used in the calibration, other high-gain antennas, as well as making electromagnetic interference measurements. Next slide, please. The next type of antenna we have is the reflector antenna. When the antenna is used for transmitting a signal, the signal from the feed comes out of a dipole or a horn antenna to focus the wave on the parabola. It means that the waves come out of the focal point and strike the paraboloidal reflector, which gets reflected as a collimated wavefront. As a receiver, whenever an electromagnetic wave hits the shape of the parabola, the wave gets reflected onto a feed point. Although, again, this is only one example of a reflector antenna. There are many other configurations for reflector antennas, and this is the best example here. Next slide, please. Then we have the lens antenna, which uses convergence and divergence properties of a lens to transmit and receive signals. These antennas consist of a dipole or horn antenna followed by a lens. The size of the lens used depends on the operating frequency. The higher the frequency, the smaller the lens. Due to this lens, the antennas that are used at the higher frequencies and they can be quite bulky at low frequencies. Next slide, please. So the next type of antenna we have is the microstrip antenna. Microstrip antenna consists of a very thin metallic strip placed on a ground plane with a dielectric material in between. The radiating element and feed lines are placed by the process of photoetching on the dielectric material. Usually, the patch or microstrip is chosen to be square, circular, or rectangular in shape for the ease of analysis and fabrication. It has a broad radiation pattern and a narrow frequency bandwidth. Next slide, please. So the last type of antenna we have is the array antenna, which is a set of two or more antennas. The signals from the antennas are combined or processed in order to achieve improved performance over that of a single antenna. An example of this kind of antenna is the Yagi-Uda, which consists of a single driven element, typically a dipole or a folded dipole antenna. Other elements are parasitic, which help to reflect the energy in a particular direction. Again, there are other configurations for this antenna which are not discussed in this presentation. And that's all for the types of antennas.
So, hello everyone. I am Alden Evangelista and I will be discussing about our build our own antenna. So, first, we define what is our Yagi Wi-Fi antenna. So, Yagi Wi-Fi antenna is a directional antenna that improves radiation in a single way, and such radiation can be either transmission or reception of energy, such as cell signal. It is designed to work only on FM channel, and it has the best gain for its sizes and a correspondingly narrow main lobe. So, it consists of a driven element such as dipole or folded dipole and additional parasitic elements, typically a reflector and one or more directors. So, a Yagi antenna is used for communications in a medium range of 3 to 5 miles between 2 points. It can also be used as a bridge antenna to connect clients to an access point. So our group decided to build this antenna because we know that Philippines has one of the worst internet connection. So the function of our Yagi Wi-Fi antenna is to greatly extend the ability to reach Wi-Fi access points. So what are the benefits of this Yagi Wi-Fi antenna? So the benefits of this Yagi Wi-Fi antenna is first, it is inexpensive. It can only be made by wood and wire, and it provides high gain and directivity. Second is it provides internet connectivity from one building to users in our remote house or office. Third is providing internet connectivity from one high-rise building to another across town. Next is to provide internet connectivity from an onshore location to users on an island. And lastly, is sharing connectivity between two locations which can be linked by cable. So we also designed Yagi Wi-Fi antenna because design depicted here can be built easily and it gives a great result. It can be made by computer designed, made of wood and wire, and provides high gain and directivity. It is directional, which means favoring Wi-Fi signals in one direction and rejecting interference from the sides or behind the antenna. The 15-element Wi-Fi antenna provides over 15 decibels of gain, while the larger 20-element Wi-Fi antenna provides over 17 decibels of gain. Front-to-back ratio for both antennas is about 22 decibels. So the figure also shows each antenna element from the reflector, element 1, which is positioned at 0 millimeters, to the last director. So in making this Yagi Wi-Fi antenna, we use an app in determining the length and position. So that concludes our presentation. Thank you for listening.